Okay, so we're going to take a look at hypothesis testing. Before you go through this video, make sure you look at the textbook. They give a lot more information. They can fill in the gaps. However, they do something we're not going to look at. They look at something called the critical value approach to hypothesis testing, as well as the p-value approach. And we only focus on the p-value approach for our course because that's the one that more and more people are actually using. So while the book is good to fill in some of the notation and extra information, make sure you're only focusing on the p-value approach to hypothesis testing. Right, the general idea here is to apply a scientific method to decide whether or not you can adopt a new claim in place of one that's initially assumed. And I'm always going to go through a four-step process. In my experience, the notation and the language of hypothesis testing does not make much sense to people until you actually get into doing examples. So that's why we're going to pretty much peel through this quickly and get right into the examples. All right, so the first step, formulate the hypotheses. All right, we start with a null hypothesis, which is some value for the mean or proportion that we assume to be true. It may have been based on a study from a year or two ago, or it may be some kind of target that a company aims for in manufacturing, but the null hypothesis is going to be the hypothesis that we start with. And it's assumed as true to start. In fact, we're going to do our procedure for the test assuming that the null hypothesis is true, and basically use the test procedure to measure how much evidence there is against the null hypothesis and in support of the alternative hypothesis. The alternative hypothesis will basically just take the sign of the notation and change it into either a less than or greater than, or occasionally a not equal to, although usually the not equal to version is dealt with in a confidence interval. And then instead of a 0 as a subscript, you'll see a 1 as a subscript in our book for the alternative hypothesis. Then step 2 is where we actually do some arithmetic. What we do is we take our test statistic formula, either for the mean or the proportion, and what these are basically converting either our sample mean or our sample proportion and standardizing them. It's basically trying to use the idea of a z-score, taking the data value, subtracting away its claimed mean, so the mu0 and the p0 are whatever value is claimed from the null hypothesis, and we convert into these standardized versions assuming that the null hypothesis is true. We've used the hypothesized value for the actual mean. So basically, if the null hypothesis is actually correct, we expect these test statistics to be relatively close to 0. If the alternative hypothesis is correct, we expect these test statistics to either be positive if the alternative was greater than, or negative if the alternative was less than. So after we have our test statistic, we need to kind of measure the probability that we could have got this kind of test statistic by chance alone under a true null hypothesis. So we find what's called a p-value. P-value measures the probability that we could have obtained that result in our sample, even if the null hypothesis had been true. The general rule is the lower the p-value is, the stronger the evidence is against the null hypothesis and in favor of the alternative. However, for our course, I'm going to give you a specific rule that you can follow to make your conclusion, because you're not going to be the statistician to make the judgment call. You're just going to follow a rule for comparing the p-value to a specified level of significance, or alpha. The level of significance is actually a probability of making a certain error. Now, because of the time constraints of this course, we're not going to have time to get into these errors, But that's where the alpha comes from. It's an accepted probability that you take of making a certain type of error. And unfortunately, the lower you make alpha, the lower the probability of one type of error. You're then dealing with a higher probability of a different type of error. So here's the rule that we're going to use. If the p-value is less than or equal to the provided significance level, or if p is less than or equal to alpha, there is sufficient evidence to adopt the alternative hypothesis. If the p-value is greater than the significance level, then we're going to say there is not sufficient evidence. Notice the only word that's different in those two is not appears in the second one. The conclusions we write are going to sound very similar. Okay, so like I said, most of the time this stuff doesn't make sense until we actually jump into it and start doing problems. So let's take a look at a first problem. A health food company claims a serving of its turkey meatballs has 415 calories. A consumer advocate group collects a sample of 91 of the servings and finds a mean of 422 calories with a standard deviation of 27 calories. At the 5% significance level, is there enough evidence to claim there are more than 415 calories per serving in the meatballs? On a test, certainly for the first problem dealing with hypothesis testing, I would separate this problem out into parts. So what you could expect maybe is a part A that says formulate the hypotheses. I would ask that you use the same notation from class. So we're going to use an H0 for the null hypothesis and an H1 for the alternative. Now I've got to decide that this is a problem about a mean. This is not a proportion, this is a mean. It's giving me numerical data of interest, and it actually says, we're concerned with a mean of 422 calories in our sample. So we're going to make a claim for the null hypothesis that our population mean is equal to, well, let's think which one of these would be the initially assumed true value or the target value. That would have to be the 415 calories that the company tries to say their product contains. Maybe it's stamped on the box, or maybe it's just the target that they use to manufacture. This consumer advocate group is wanting to answer the question, is there enough evidence to claim that there's more than 415 calories? So the alternative hypothesis is going to be that the mean is greater than, that the mean is actually greater than 415. So the first step, the hypotheses, really just to sort of set up the hypothesis test. Here's where the real work begins. Part B, what I'd ask you to do is show the steps or work in finding the test statistic. I'm going to start just by copying the test statistic formula down. And then we can plug our values into it. So X bar, the sample mean here was 422, right? It said that in a sample of 91 of the servings, the mean was 422 calories. We would subtract, remember this value right here, this is the one from the null hypothesis. That's the 415 calories that the company claims is in it. The S is the standard deviation, so here the sample standard deviation was 27 calories. And we had a sample size of 91, so this would be over radical 91. Now, when I punch this up in the calculator, 422 minus 415, if you want to just call that 7 in the numerator, that's fine. But if the numbers were uglier or we just want to punch everything in, we're going to put parentheses around the numerators. And then divide by, we'll start new parentheses. Some calculators just need the one parenthesis at the end, others need two. So this is how I could punch this into the calculator and get the test statistic. Now if I punch this up, I'm getting about 2.473. So if you don't have your calculator now, come back to this, see if you can get that as the test statistic. But notice the sample mean 422 was larger than the null hypothesis claim of 415, so it's going to be a positive value. So 2.473 is my t test statistic. For part C, what I ask you to do is a sketch and find the p-value. So remember, the t-curve looks very similar to the z-curve. In fact, by hand, I can't draw it any different. Centered at 0, and 2.473 would be out on the right tail. The p-value is going to be the area to the right of that, because we were doing a test to see if the mean was actually greater than the claimed null hypothesis value. So the question now becomes, how do I find or estimate this p-value? Turns out, in a t-test here for a mean, we have to estimate it. So we're going to have to estimate the p-value using table 6. All right, so 2.473 is my test statistic. I'm going to advance here to get to table 6. Here's table 6. Now here's how I got to do this. I'm going to go down and look for the 90 degrees of freedom, because in this problem the sample size n was 91. Subtract 1 from the sample size, you get the degrees of freedom. I'm going to take a look at these values across the 90 degrees of freedom row, and every once in 1,000 times we end up with our test statistic right in there exactly. But 999 times out of 1,000 we don't. So what we have to do is look for two values like these, 2.368, which is a little bit smaller than our test statistic, which was 2.473. So the 2.473 would be in the middle of those two. So what I can do is scroll to the top of these two columns here. To see what those two right tail areas would be. And I know that my p-value has to be between these two numbers. So again, we go down to the 90 degrees of freedom, scroll over to find the two values that our test statistic is in between, and scroll up to the top to find the two values that our p-value has to be in between. So now I know that the p-value has to be between 0.005 and 0.01. So that means there's a very small probability, a little bit more than 0.5%, but less than 1%, that this sample mean and this test statistic could have occurred if the null hypothesis had been correct. Part D, I'm going to ask for the conclusion, and we got to write our conclusion always in the context of the problem. So in this case, my p-value, which we said is less than 1%, the p-value is less than the significance level, because my significance level here was 5%, or 0.05. The problems will all say something like this at the 5% significance level, and that's telling me alpha equals 5% or 0.05. So I know that my p-value has to be smaller than that, and this is when we go ahead and adopt the alternative. We're going to reject the null hypothesis, and we're going to adopt the alternative. Now, the way I write my conclusions, it's basically this. I always say at the and give the significance level, so at the 5% significance level, now we're going ahead and adopting the alternative hypothesis, so there is enough evidence to claim. And now I'm just going to use language appropriate to the problem to identify the alternative hypothesis, which was that the mean amount of calories in the entree or in the meatballs is more than 415. So there is enough evidence to claim the mean number of calories in the meatballs is more than 415. So this hypothesis testing procedure, the first time people do it and see it, they really don't like it. But with practice, people start getting more comfortable with the process and end up, for a lot of people, end up doing pretty well with it as a topic. So let's see if we can go through the same set of steps for the next example. All right, so the mean wait time in line at an amusement park ride was 18 minutes in 2014. A new loading and unloading plan was implemented. In a sample of 110 rides for this year, the mean wait time was 16.9 minutes, with a standard deviation of 13.2 minutes. At the 5% significance level, can we claim the new procedure was effective at decreasing the mean wait time? All right, so again, I'm going to go through the same 4 steps. First, let's do our hypotheses. The null, the alternative. Well, here's the null hypothesis because it's telling me what a previously known value was. So the null hypothesis here is that the mean wait time is going to be 18 minutes. I just use mu equals 18. The alternative has to be either mu is not equal to 18, less than 18, or greater than 18. Got to use the language of the problem to figure it out. It wanted me to test to see if it's effective at decreasing the mean wait time. So that means we're testing to see if the mean is now less than 18 minutes. The second step is the test statistic. So again, this is about the mean. We're going to copy down the formula for the mean. I'm going to plug in my values. So 16.9 was the sample mean, minus 18, that's the value claimed in the null hypothesis. S, the standard deviation, was 13.2, divided by square root of the sample size, which was 110. All right, so I'm going to do this the same way as before with parentheses around the numerator. Hit divide by and do parentheses around the denominator. And I'm getting a test statistic of approximately negative 0.874. Now notice last time our test statistic was 2 point something, much farther away from 0. This one, the test statistic is less than 1 standard deviation away from the mean because it's negative 0 point something. So this time we got a test statistic that's much closer, at least as a z-score or t-score, much closer to 0. All right, so C, we're going to sketch the picture. And we would want the area to the left of negative 0.874 this time. I'm going to go to table 6 to try to approximate the p-value. When I go to table 6, it has all positive t-values. I'm just going to take advantage of symmetry and say that because the t-curve, just like the z-curve, is symmetric, that I can find or approximate the area to the left of negative 0.874 by looking at the area to the right of positive 0.874. Now the degrees of freedom would be 109 because the sample size was 110. We're just going to go with the closest one on the table, so 100 degrees of freedom would be closest. All right, we're going to ignore the negative. We got 0.874, which is bigger than 0.677. It's bigger than 0.845, but it's smaller than 1.042. So our test statistic is in between these two. So again, if we scroll up here, that means our p-value is in between these two. It's between 0.15 and 0.20. Well, that's telling me that there's between a 15 and 20% chance that that test statistic could have happened by chance alone if the null hypothesis was true. That's not really giving me very strong evidence against the null hypothesis in favor of the alternative. So for part D, the conclusion we got here, our p-value was larger than the significance level. In this problem, they said the 5% significance level again. P-value is larger than that, so I write at the 5% significance level, this is the only word that's different. There is not enough evidence to claim. Now, the alternative hypothesis, right, we're going to say do not adopt the alternative. The alternative here was that the new system is effective at decreasing the wait time. So I'm saying there is not enough evidence to claim the new method decreases wait time. Right, so had we got a real low p-value and like problem 1, the p-value was smaller than alpha, we would go ahead and adopt the alternative. All I would do is erase the word not in there. Your conclusions would be very similar, it's just one word different. In fact, the next example, what I'm going to do is write the conclusion ahead of time just with a blank, and then we'll basically use the test to figure out whether I leave it blank or fill it in with the word not. All right, so we're going to take a look at a proportion here. In 2009, it was determined that 29% of the students at a college had used illegal drugs that year. The college attempted to lower that rate with education programs. A survey was done in 2015, and out of 408 students, 102 had used illegal drugs that year. At the 10% significance level, has the proportion of students using illegal drugs decreased since 2009? Then, how about at the 1% significance level? Right, one thing to pay attention to is, again, we're going to have to go through a hypothesis test procedure. What you can't do is say 102 out of 408, that's 25%. So sure, 25% is less than 29%. So yeah, it's decreased. The 29% was a value established in 2009. In this 2015, we've just collected a sample. So 25% as a sample proportion doesn't mean that that's the same as the population proportion. So you've got to go through the test for one of these problems. Now again, I'm going to do a big space here. I know that my conclusion is going to be at the 10% significance level, there either is or is not, so we'll leave a blank there, enough evidence to claim the alternative hypothesis, which here, let's see what the alternative hypothesis would be. The null hypothesis is going to be that the proportion is equal to the previously known proportion, 0.29. So this is our previous value that we're going to assume to be initially true. The alternative hypothesis, we're supposed to do a test to see if it's decreased since then. So it's going to be that the proportion of students using illegal drugs is less than 29% or less than 0.29. One of the things I like to do is steal the phrasing from the problem. So I'm going to say, I know it's at the 10% significance level, there is blank, because maybe I'll put the word not in there, enough evidence to claim the proportion of students who use illegal drugs has decreased since 2009. All right, let's actually do the test to see what our conclusion is going to be. So this was A, the hypotheses. Now, keep in mind, it should be pretty easy to identify this is about a proportion. Problem comes right out and uses the word proportion, but it's also talking about the percentages or proportions of characteristics, basically. Whether you use illegal drugs or not, that's not a numerical variable, it's categorical. All right, so for part B, we are calculating our test statistic. If you want to go back to one of the first slides, we have the test statistic formula. But it's taking our sample proportion p hat, subtracting the claimed proportion in the null hypothesis, and dividing it by the standard deviation of a sample proportion, assuming p0 is the value, p0 times 1 minus p0 over n. So if I plug the values from this problem in, let's see, p hat off to the side here, it was 102 people out of 408. So our p hat, our sample proportion, is 0.25. The p0 would be the 0.29 divided by the square root of 0.29 times 1 minus 0.29 would be 0.71 divided by the sample size of 408. The way you can punch this up in the calculator, parentheses around the 0.25 minus the 0.29. Then just hit divide by the square root. Should open up a parenthesis for you, and you can type in 0.29 times 0.71 divided by 408. End your parenthesis to end the square root. All right, I got negative 1.78 out of that. If you don't have your calculator now, go back, give that a try, see if you can come up with that value. Now we got to move on to part C, which is sketching the curve and finding the p-value. All right, we're going to go to the left of negative 1.78 because our alternative hypothesis was a less than. We wanted to see if the proportion had decreased. Now I'm using my table 5 because we're dealing with a z value. So negative 1.78, it looks like the area to the left is 0.0375. So our p-value is 0.0375. It's easier to find the p-value for one of these proportion ones because we actually get a z-score out of our test statistic. So part D, the conclusion, it first asked us about the 10% significance level and then the 1%. So we're starting with the 10%. In that case, the p-value would be less than alpha if alpha is 10%. So that means we reject the null hypothesis, we adopt the alternative. So my phrasing is fine without the word not in there. So at the 10% significance level, there is enough evidence to claim the proportion of students who use illegal drugs has decreased since 2009, because the p-value is less than your significance level. So if somebody had told you to use a 10% significance level because they were okay accepting a 10% chance of a error where they reject a null hypothesis that's true, here's your conclusion. But on the other hand, the other part of this problem said, well, what about at the 1% significance level? So if the significance level had been 1%, alpha would equal 0.01, and then your p-value of 0.03, whatever it was, 0.0375, would be larger than your alpha. So you'd have the opposite conclusion. At the 1% significance level, you would say there is not enough evidence to claim, then the rest of it would be the same, that the proportion of students who use illegal drugs has decreased since 2009. The difference there in setting the different alpha levels, the levels of significance, it's sort of like in trials. If you're doing a criminal trial to convict someone of armed robbery, there's a larger burden of proof than if it's a civil suit where the victim of the robbery is suing the person for monetary restitution. One of them is a burden of proof. You have to prove beyond a reasonable doubt. The other one is simply a preponderance of the evidence. So in this case, if they said 10% significance level, then yeah, the p-value is low enough where there's enough evidence, reject the null hypothesis, adopt the alternative. But if the significance level was 1%, we would end up writing the opposite conclusion. All right, so one more problem to try here. One where we have some options because it's a not equal to. The proportion of capacitors manufactured to go into a PET ID microchip that are defective has been 3% for many years. A test is to be done again at the 2% significance level to see if the percentage of defective capacitors has changed. Out of the 800 tested capacitors, 10 tested defective. Okay, so I mean, one approach to this, some people would just say, well, 10 out of 800 is less than 3%. So let's just do a test to see if it's decreased. But we have to follow the test following the original phrasing of the problem here. So what we'd have to do is say, for part A, the null hypothesis is going to be that the proportion of defective items is still 3%. And the alternative is that the proportion of defective items is not 3%. Now, if you're going to do this with a hypothesis test, you basically can go through the same exact setup, go through the same procedure, except when you do your p-value, you would have to do what's called a two-tailed test. You would end up doing the area to the left of your negative test statistic, and then you would double it because you'd have to also accommodate for the area to the right of the positive version. Most people don't like that. So what I tell people to do is use a confidence interval if you'd like to, if and only if the alternative hypothesis is not equal to. So in this case, since we have a not equal to for the alternative hypothesis, we would be able to use a confidence interval. So here's what we could do. Let's take a look at our confidence interval formula, p hat, plus and minus our critical z-score. So this is our confidence interval formula. All right, in this case, p hat would be 10 out of 800. Right, let's see, is that right? Yeah, 800 tested, 10 tested defective. So that's a 0.0125. So 0.0125 for my p hat. The 2% significance level would correspond to a 98% confidence level. Remember that alpha, we had experienced that in chapter 9 doing confidence intervals. When they said 95% confidence interval, we made alpha 5%. So here it's the other way around. Alpha is 2%, so 98% is the confidence level. So using table 5, 98% confidence level gives me 2.33 for the critical z value. Then I have the square root of 0.1250 times 1 minus that, which would be 9850. All right, we're starting over with this square root. Square root 0.0125. 1 minus that is 0.9875 over n, which is 800. So remember, with the confidence intervals, we first calculate this margin of error. So 2.33 times the square root of 0.0125 times 0.9875 divided by 800. I'm getting 0.0092 if we round it off to 4 digits. Now I'm going to use the minus. Using the minus gives me 0.0033. Now using the plus gives me 0.0217. Now check out the null hypothesis value. The null hypothesis was that the proportion is 0.03. Is 0.03 a value between the left endpoint and the right endpoint? Well, no, this interval is entirely below 0.03. So what we would do is say at the 2% significance level, the proportion of defective capacitors is not 0.03 because 0.03 is not in our confidence interval. If it had fallen in our confidence interval, then we would have said at the 2% significance level, there is not enough evidence to claim the proportion of defective capacitors is not 0.03. So to be perfectly honest, it's unlikely I'm going to make you do a not equal to hypothesis test. Much more likely it's going to be either a less than or greater than. So check Blackboard. I'm going to put up a list of problems to try for hypothesis testing to replace the books because I'm not thrilled with the questions in the book. So don't worry about the homework problems from the textbook for this material. Just focus on what I post on Blackboard. Good luck and have a good night.